value depends on what n is. If n is 1, if you're the first energy level, there's only one possible L, that's 0, because that's n minus 1. Let's say that we're in the fourth energy level. That means n equals 4. So the L values would be 0, 1, 2, and 3. So L always starts at 0 and goes up to L to n minus 1. Okay? The L values have special names. And I think this will come back to you. If L is 0, that's called S. And then P, D, and F from 0 up to 3. If L equals 4, it's possible. Theoretically, it's possible. We don't have any evidence for that sum level from things on the periodic table. But theoretically, you could have an L value of 4. That would be called G. So they just kind of go alphabetically from F after L equals 3. G, H, I.
You can't get me some of the A, B, C.
Yeah, what if they go all the way to whatever S is?
Yeah, then I don't know what, I guess. You're never going to go above I, though. Sometimes, exam writers, they'll be busters, and they'll put like a G or an H on there. You're not going to go up to J or P or whatever.
P, Q.
Not going to go there. Okay, so before we do the other two quantum numbers, there are 4 quantum numbers. We've seen 2 of them, N and L.
Oh.
You'll remember these 2, maybe. The where L equals 0, that sublevel is just spherical in shape. That's it. It's just a sphere. It's very simple. That would be an S sublevel. You can have 1s and 2s, where their electrons could be on the 1s level or they could be on the 2s level. They're never going to be in between. That also is, consistent with what Bohr said. Bohr said that you can have energy levels that electrons can be on, but they'll never be in between. It's the same thing as what the Schrodinger model is. There's Schrodinger called them nodes. A node is a part of a wave that's not moving.
Is that why in Pitch Perfect she said that she had nodes?
Probably.
Probably
I've
not.
never seen Pitch Perfect, I don't know.
Except for nodule.
Good movie?
Yeah, it's classic. It's a classic.
Nice. Okay. Now if L equals 1, those are the P. That's the P sublevel. The P sublevel is broken up into 3, what we call orbitals. Orbital is going to wind up being represented by the 3rd quantum number, the one we haven't seen yet, that's M sub L. But, so the P, this would be considered 1P sublevel. But really it's made up of 3 different orbitals. One dumbbell shape going along the x-axis, one going along the y-axis, which is perpendicular to the x, and one along the z-axis, perpendicular to the x and y. So we would say that the P sublevel contains 3 orbitals. An orbital is an arrangement for part of that sublevel that can hold 2 electrons. So in this region, 2 electrons could be found. In this region, 2 electrons can be found. And in this region, 2 electrons can be found. So the P sublevel, no matter what energy level, the P's can hold 6 electrons. But they're broken up 2, 2, and 2. Same thing for the S's. The S can only hold 2 electrons. There's 1 orbital there, it can hold 2 electrons. So there's S's and P's. That's where L equals 0, L equals 1. And when L equals 2 and 3, they get more complex. Here's a D. You don't need to copy this down. I mean, if you want to look at pictures of this on your spare time or whatever, of course it's in the book. I hope you can find something better to do in your spare time. But if you wanted to. They're kind of clover-shaped. 4 of them are clover-shaped, and then one of them is this oddball donut with the dumbbell. Keep in mind that Schrodinger was not sitting down with his artist friend and they were saying, oh, how should we make these look? These are all solutions to his equation. Okay, this is what the equation kind of spit out. Each of these, there's 5 different possible shapes within the D sublevel. These 5 shapes are called orbitals. 5 different orbitals in the D. Each of these can hold 2 electrons. So as complex as that looks, like this thing right here, looks complex, it's got room for 2 electrons. I know it looks like it could hold more, but it doesn't. It's got 2. There's 2 in this, 2 in this, 2 in this. So all D sublevels could hold 10 electrons, 2 in each of those shapes. Then the F's are even more complex. Each of these has room for 2 electrons in it. You probably wouldn't be asked anything ever about D and F shapes. You would be asked about S and P shapes. Often they'll ask on the AP exam, what is the shape of a P orbital? You'd say dumbbell shape. If they ever asked about D, you want to say clover shape. Okay? And then F, they're never going to ask about F. Honestly, when I was in college, I never saw a rendering of an F. We were just told F is complex. The first time I taught this course, the good old Zoom dolls enlightened me as to what the F's look like. You can find F images now that we've got computer modeling that helps us to visualize stuff. But yeah, when I was in college, I never saw F's.
What did you think it looked like when they said it was complex?
I didn't know. Yeah, I mean, I wasn't at all surprised to see this.
The top's weird.
Yeah.
Would G
Yeah.
be in like 4D?
What's that?
Would G be in like 4D?
4D is like.
I don't think
I
so.
don't think there's such a thing. Like, what are you gonna do? Smell it? Like, how can you put another X on?
Theoretically, yes. I don't know that there's ever been any evidence for an electron becoming excited
Make
before
another
G.
one.
Might be though. I mean, there's no reason that we have to stop at F.
No, I guess I get that. I was just thinking of the elements of that item.
Yeah, no, we don't go that high. Ground state just takes us to F's and that's it. We need another full row on the periodic table to get G's. Okay, here's the third quantum number. I call this the orbitals. The magnetic quantum number is what the big guys call it. Values of this depend on L. Within a sublevel, how many orbitals are there? If L is 0, like for the S's, then there's 1 orbital. It's got an M sub L value of 0. Doesn't mean there's no orbitals, there's 1 with a value of 0. If L is 1, that's the P's. M sub L can be -1, 0, or positive. M sub L, yeah, that's a little L. Subscript L. Yeah, I just say sub L. You're not making fun of the way I talk, are you?
What's the dot dot dot? M sub L, whatever it is.
Oh, this just goes integer values from -L to positive. Okay. It's an L. I'm sorry. My font. So Ellen in Pitch Perfect, is it about singing? I assume
Yeah,
it's
yeah,
about
yeah.
singing. She got notes on her vocal cords.
Yeah.
So you know vocal cords are meant to vibrate.
Like nodules.
And so if you have a node, that prevents the vibration from happening, so your voice doesn't sound the same. I think the same kind of thing is here. The node is remember, electrons are being described as waves. So if you have a place there where a wave cannot move or can't be, then that's the electron can't be there. And so yeah, Ellen, it was the same thing. Same thing. Okay, fourth quantum number is very simple. I want you to remember, let's see. Write one more thing down for yourself too. Each orbital can hold 2 electrons.
Oh my gosh, is that why there's
Yeah, that's going to give us the up-down arrows. You remember doing the arrows. Now, because orbitals are these little clouds or regions, electrons are negative particles. 2 negative particles don't like to hang out together. That's why we require, not we, it's not like we're trying to design this is what we observe. Electrons must be spinning with opposite spins. If you have a charged particle spinning, it's going to have a certain magnetic field. And so the other electron in the same orbital must be spinning the opposite direction so that those will have opposite magnetic field. It doesn't quite attract them to each other, but allows them to hang out in a confined space. So each orbital couldn't, oh, I guess I had on the next slide. The only way is for them to have opposite spins. So the last quantum number is m subscript s, ms. They can be positive 1/2 or negative 1/2. Those are the only 2 possibilities for m sub s. One other slide with some examples on it, and we'll be done. Here are 5 sets of quantum numbers. Some of these are legitimate. Some of them have a problem. The first set, you're given all 4 quantum numbers, 3, 3, 0, negative 1/2. Is that set of 4 quantum numbers legitimate, or is there something wrong with it? What should I? What about it?
Does it have to be less than that?
That's right. This number right here. If n is 3, L has to be 0, 1, or 2. It goes up to n minus 1. So 3 is out of the range for the third energy level. That's why in the third energy level, there's 3p, 3s, 3p, and 3d. There's no 3f, there's no such thing. Because f would mean that L equals 3 and it can't exist. What about the second set? 4, 3, 2, and negative 1/2. Yeah, right. N is the energy level. L is the sub-level. M sub L is the orbitals. This is the orbitals are the sublevels broken up so that the orbitals and the sublevels broken up So that